Welcome to Monash Deep Neuron Semester 2 2020 Project Showcase. I'm Rebecca and I've had the privilege of leading this extremely talented group of students over the past year. I'd like to thank you all for joining us tonight and extend a special welcome to our supervisors, alumni, and friends of the team, both from industry and Monash University. Before we begin, I'd like to quickly acknowledge the traditional custodians of the various lands on which we work today, and the Aboriginal and Torres Strait Islander people participating in this webinar. I acknowledge the contributions of Aboriginal and non-Aboriginal Australians to the inclusion and empowerment of all people in the country we live in and share together. I pay my respect to elders past, present, and emerging, and recognise and celebrate the diversity of Aboriginal peoples and their ongoing cultures and connections to the lands and waters of Victoria. Additionally, in respect and in the spirit of Remembrance Day being honoured today, I'd like to also pay our respects to all of the fallen, all of the wounded, and all who have served in conflicts over the last 100 years. Today, as we should every day, we remember those who volunteered, sacrificed, served, fought, and died for our freedom. We thank you and we salute you as we salute those who made the ultimate sacrifice for our freedom. We will never forget. We will remember you. Tonight, we'll be hearing from all our project managers about the work that their project teams have completed over the last season. But before that, I'd like to give a brief introduction to the team for those of you who aren't too familiar with who we are and what we do. And I'd also like to spend some time congratulating some of our students who are finishing up their courses at Monash this semester. A reminder that the formal part of our evening will be followed by a Q&A session with all our project managers, in addition to members of our executive management team, both of 2020 and 2021. If you have questions at any point during the evening, please do send them through using the Q&A function, which you'll find located either at the top or bottom of your Zoom window. For those of you who aren't familiar with Monash Deep Neuron, we're a student team comprising over 50 students. We have students studying from a range of different degrees and have students studying bachelor's, master's, and PhD level courses. As a multidisciplinary team, we have students studying commerce, engineering, IT, and arts, just to name a few. As a team, our vision is to empower, engage, and educate students, researchers, and the community about artificial intelligence and high-performance computing. We empower and engage the students on our team by providing them with opportunities to work on projects across a wide range of fields in applying deep learning and high performance computing to these fields in collaboration with researchers at Monash University. In addition to our project work, we're passionate about engaging with and educating the community about both these fields of AI and HPC. Both these fields are rapidly growing, and we aim to not only educate people about how these tools can be used, but also open up conversations about how we can use these tools ethically. We strive to achieve this through our events, including our hands-on workshops and our industry events. And you can stay up to date with all our latest events by following us on Facebook and LinkedIn, and also by signing up to our mailing list on our website. Before we move on to hearing the latest updates from our project teams, we'd like to take some time to congratulate our team members who are completing their courses in the coming months. I do encourage you to send through your congratulations in the chat. From our HPC team, we'd like to thank Luhan, who has not only been part of two of our project teams, being Microscopium Deep and the Drone Project, but has also been serving as our HPC lead over the past year. Thank you, Luhan, and congratulations on completing your honours. Moving on to our deep learning branch, a thank you and congratulations to Sahil, who, as you can see, has worked on not just one, but 3 of our projects, these being noise to self, aerodynamics, and microfluidics. Sahil has additionally also led our sponsorships team over the last year, so thank you for all your hard work, Sahil, and congratulations on finishing your course. Continuing with our deep learning students, from our CT team especially, we'd like to wish good luck and congratulate both Stephen and David as they complete their undergraduate courses. Every one of you have put in so much work and effort, time and effort into the team. We really can't thank you enough for all your work you've put in, especially to your projects. So from all of us at the team, as well as from all the researchers that we collaborate with, a big thank you and good luck for any assessments you have waiting for you. and we can't wait to see what all of you do next. We're now going to be moving on to hearing the latest from our project teams. Each project manager will be presenting the work on behalf of their whole team, which has been completed over the last project season. As we're holding a Q&A session after the formal close of the evening, we won't be taking questions during the presentations. However, as I mentioned before, all the project managers will be available to answer any questions you have during the Q&A. I'd encourage you to continue sending questions through, even during the presentations, and we'll make sure to answer them during the Q&A. It doesn't matter if you think you have a really simple or really complex question, we'd love to hear from you. If we don't get to answer your question, do send us an email and we'll try to get back to you as soon as possible. I'd now like to hand over to Luhan, our HPC lead, to introduce our first project team.
Thanks, Beck. I'm Luhan. I'm the high-performance computing lead at Monash Deep Neuron. Currently, the HPC branch is working with Monash Drone Discovery Platform to develop a more efficient drone image processing pipeline. Yusuke, who is our project manager for the drone project, will now give us a detailed presentation on what we have been working on during 2020 and our future plans for the next year.
Thank you, Luhan. Hi, my name is Yusuke. We have 10 people working on this project, including myself, Luhan, Angus, Shaurya, Sam, Mohit, Aisha, Raj, Christopher, and Simon, who is also our supervisor. Now I'm going to present some progress of the drone photogrammetry project. Drone photogrammetry is about the image processing of the drone images to obtain reliable information about physical objects. Here on the slide is the workflow of the project. Pictures taken by drone contain coordinate information such as position and angle, and we use two software to process the data. OpenDrawMap uses the coordinate information to do 3D reconstruction. Then the data is further processed by Cloud Compare to calculate important information about the object, such as normal and curvature. The aim of this project is to build a more efficient drone image processing pipeline, as the existing software such as OpenDrawMap and Cloud Compare do not fully exploit the potential parallelization of the computational workload. Parallel computing refers to breaking down large data sets or programs and processing them at the same time for efficiency. Processing images with parallel computing requires many computational resources, so it should run on high-performance computer. High-performance computer is formed by connecting many computers, and it can solve large and complex problems. Students in Deep Neuron have access to the high-performance computer owned by Monash University, and we would like to implement a software interface that enables the image processing pipeline to utilize the high-performance computer. It can potentially speed up the computation. There are mainly 3 steps to improve the code performance: analysis, parallelization, and optimization. We need to investigate the algorithm used in the software and understand how the data is processed on multiple tasks. We do this by looking at the source code or using a debugging tool. In terms of parallelization, we tend to look for large loops that repeat the same computation, and we'll add on some codes to make it process simultaneously. We also need to check if the same data go through multiple tasks, because the tasks cannot be processed at the same time if they are dependent on each other. And finally, we can optimize the code performance by checking the time the code takes to process the data or the CPU usage. For this project, the team is currently investigating the established code of the software and understanding how it's doing what it's doing. We found that both OpenDrawMap and Cloud Compare can run on multiple cores on a single computer. The team is still spending time on investigating the software, as the software involves complex mathematics and programming tool which we're not very familiar with. Once we have some good understanding about how the established code works, we can extend the parallelization and run on multiple computers using MPI. MPI is a library to control the messages between computers. We can take advantage of MPI if we know how data is processed in each of the software. We could also modify the code to run on GPU or compile the code on Intel compiler instead of GNU compiler to improve the performance. The diagram on the left is the possible architecture of the parallel computing we want to achieve. This is all about the project at this point. Thank you.
Hello, my name is Mitchell, the Deep Learning Lead of Monash Deep Neuron. This semester, some of our members have been interning with the Data Science and AI platform and working on projects with them. We will first be hearing from Emily, who has been working on the digital phenotyping project, one of a collaboration with the Turner Institute to predict sleep and physical activity from smartphone data.
Thanks, Mitch. I'm Emily, and I'm from the Digital Phenotyping Project, one of the Data Science and AI platform internships of this semester with my team at MassSal. This project has worked in collaboration with the Turner Institute in an attempt to uncover whether mental illness can be identified or anticipated through passive and active smartphone data. As a background, digital phenotyping is a field of science that explores moment-by-moment quantifications of individual human phenotypes and characteristics using data from digital devices. In recent years, research has shown that predicting human psychological features from digital data has seen high levels of success and is a rapidly growing area of interest. This methodology of data collection also provides a non-intrusive alternative for researchers and medical practitioners to conduct experiments and provide diagnoses for their patients. The process starts with a study design where the types of questions and data are decided and specified. This is then distributed to participants, normally in the form of an app. Participants are then required to fill out surveys and questions, as well as keep the app running on their devices for it to self-report data. This data is then extracted and processed for analysis. There are two main types of data that are collected from these experiments, and those are active and passive data. The active data are symptom self-reported results, while passive data is inclusive of GPS, accelerometer, and call logs. For our goal, we chose to focus on predicting the stress levels of an individual through measurements collected from their smartphone data. The Turner Institute has been working on an application that will collect smartphone data from participants for their own similar study, but until that is complete, we were introduced to a similar dataset called Student Life to use for our model and begin our initial analysis. This dataset was created through a digital phenotyping study that recorded passive and active data from the phones of 48 students over a 10-week period in the United States. While we were given over 50 gigabytes of data to work with, we specifically chose to focus on measurements that are not overtly involving the participation of the user to uncover the security risks and capabilities of data collection. These measurements included, but were not exhaustive to, GPS, pre-classified activity, and phone app usage. Our initial step was to provide a way to analyze the data collected, which would not only function for the Student Life dataset, but the expected one from the Turner Institute. From here, we built a data frame setup that would allow data to be easily stored and accessed for analysis when required. When accessing the data, it is broken up into folders, with each data variable containing a list of participants with stat modalities results. As an example, the GPS folder would contain a file for each participant storing all their GPS results. We chose to create our data frame in a hierarchical system to store all of these, with each system acting as its own class. The lowest framework is called the dataset, which stores the data for a single individual for a single modality. Above from that dataset are the participants. Our participant class stores all modalities for a single participant as a collection of datasets. And then finally, we have the group structure, which stores all participants for a single modality. The system we have created has the flexibility not only to load in all possible data, but can pick specific modalities and participants. Once our system was created, we began to look further into the depth of the data that we had. It was soon uncovered that the data was not quite as complete as we had hoped, with a lot of the survey data being quite sparse in terms of results and quite inconsistent in participants recording their own results. Even the passive data was not always as accurate as we had expected, with the aim, as an example, for location timestamps to be recorded every 20 minutes, resulted in a variety of time gaps ranging from seconds to hours. Pre-processing steps then had to be added to our system in an attempt to refactor data with outlier removal and time binning of the data as a way to collate results over different modalities. Our future plans are to continue the analysis on the data now that the framework is complete, and we are attempting to find measures of structure in the data via time and frequency analyses. These measures of structure may act as useful predictors in our analysis. We have begun applying a fast Fourier transform and autocorrelation measures to our GPS data, and we are currently being shown promising results in predictors. We are hoping to find a periodic structure between days in participant results to streamline a regression moving forward. When the Turner Institute's application is complete, we hope to start implementing our framework along with it and aim to see the same results reflected in their data as the one we have been using. Thank you, and I'll now pass it back to Mitch to introduce the next project.
Thank you very much, Emily. Next, we will be hearing from Pei Yao, who has been working with the Turner Institute as well, this time on conversational agents for mental health. This project looks to create a reflective listening chatbot to act as a digital confidant using Amazon Lex and Transformer architectures.
Thanks, Mitchell. Hello, everyone. I'm Pei Yao. As Mitchell have already introduced, I'm working on the Conversational Agent project, which is a new project started this semester, collaborating with Turner researchers Nina Ifanian, Chad Crizin, Nicole Robinson, and Rachel Macaulay, and supervised by Adam Morris. The overall aim of this project is to create a digital confidant that can assist the users in mental health related areas. The chatbot would be capable of providing intent-based help and directions when the user has a specific goal, which is the intent, like finding resources related to a specific topic or booking an appointment with a counselor. Also, it would be capable of carrying out supportive conversations. The intent-based part is mostly work of the other collaborators, and I'm mainly working on the conversational part, so that'll be the focus of this presentation. We decided that for providing support, we'll benefit from using an established therapy technique called reflective listening. Reflective listening is when the therapist summarizes or paraphrases the client's speech to provide a non-judgmental reflection and help the client understand their thoughts better. As you can see from the example, and you don't have to read the whole thing, this is very close to natural language processing task of abstractive summarization, where novel words or phrases are generated in the summary to capture the same meaning. And this is obviously a very ambitious task. Luckily, right now, the field of NLP and text summarization is developing very fast. And for our task, we were able to utilize pre-trained models from this project called Pegasus by Google AI, released this year in June, which is a transformer-based model specifically designed and trained to solve abstractive summarization. The Pegasus project is made of 2 stages. The first is called pre-training, where the model is trained on a web crawl dataset called C4 with around 360 million documents. And the pre-training task is recovering masked whole sentences from the documents. The input to the model would be in the format of the second row of the diagram on the bottom, and the model output would be in the form of concatenated recovered sentences, like the last row. Such a challenging task encourages the model to learn to understand the language and how to distill information, so it will more likely to generalize well in the next stage, which is fine-tuning. Pegasus was then trained further on 12 different abstractive summarization datasets. These are your normal summarization datasets that will have a source text that is long and as the input, and a corresponding shorter summary as the target. We evaluated some of the fine-tuned models with therapy transcripts, paying special attention to one trained on a dataset called Reddit TIFU, which consists of stories of people's daily frustrations and a self-written summary, usually in 1 sentence. The Reddit dataset is very similar to our task, where our inputs will also be in first person, in an informal setting, and from a wide range of topics, which is why we thought it's the most suitable for this task. The results confirmed our intuition, and the Reddit model outperformed the others as expected. So after deciding what model to use, we also built additional components to handle some pre-processing and post-processing. Aside from Pegasus, the machine learning-based summarizer, there is also a rule-based algorithm in the system called ELIZA, as you can see on the bottom right of the diagram. It transforms the input based on very simple templates and applies rules to format them into a reply. As the example shows, the underlined part is the pattern that ELIZA detects and matches with a response template, and the gray part is copied directly into the response. Coincidentally, ELIZA is also made to simulate reflective listening, so we decided to use it as a fallback mechanism when needed. The information flow is like this. When the reflective listening component of the chatbot is activated and we receive a user input, we'll check if it has enough unique words for summarization. Right now, the threshold is set at 40 words. So if the input is less than 40 words or hasn't accumulated to 40 words, the response generation will be handed to ELIZA. If it reaches 40 words, the input or accumulated input gets passed to the summarizer model. Then a few simple checks are performed on the generated summary, such as detecting if the summary actually contains words or cleaning repetitive summaries. Then the summary is formatted into a response by changing the pronoun and adding prefix by using the reflective listening technique, such as I can understand that, or it sounds like. Then we use a convenient tool called Language Tool to check the grammar and fix some mistakes before we finally pass the response back to the user. For the architecture of the chatbot, we are using AWS, so it is running on the cloud. Specifically, we're using a service called Lex to detect the user's intent, which just means what they want to do or talk about. And if the intent is general chat, the Lex would direct the input to a Lambda function, which is just a piece of code running from an isolated environment on AWS. And then the Lambda function holds all the logic from the previous slide, as well as when it's time to use Pegasus, it would make the call to an API on API gateway, which talks to our model deployed in a Kubernetes cluster. We used a deployment managing tool called Cortex, and I have included a figure on the right that explains exactly the structure of the cluster in case anyone is interested. But the great thing about using an external tool is you don't have to worry about the specifics of the architecture and managing it. So we'll leave it at that for the moment. And having only worked on this project, over the semester, and a lot of the work being more on the explorative side, there are limitations to the current state of the project. Firstly, we have found that the performance of Pegasus heavily depends on the fine-tuning dataset. The Reddit model that we chose to use works the best among the other pre-trained models provided, but because there are still differences between a specific type of social media post and therapy transcripts, which we tested on, or daily conversations, which will be the actual use case, sometimes it misses the content or interprets the sentence in a light that we don't want a supportive chatbot to. Also, the current way of formatting the generated summaries into a response is quite rigid, and a lot of time it's easy to tell that a machine instead of a human wrote the reply because of how we post-process the summary. In the future, we hope to fix those issues by firstly doing some more custom work on the model, including finding better datasets that are even closer to the task to fine-tune it on, and coming up with better post-processing strategies. Other than that, this project really have a lot of potential now that the basic foundation is set, and I'll just name a few examples that I've thought of. One possibility is adding the ability to retain more context throughout a conversation, just like a human friend would. And another is incorporating emotion detection to facilitate the generation of responses. And that's all the update for the Conversational Agent project. I'll now hand back to Mitchell.
The last platform-led project that we have is the semi-automated legal document analysis project. These interns, Sam and Matty, have been working to assist law researchers with the extracting of information within cases.
Thank you, Mitchell. Sorry, it doesn't look like my camera is wanting to turn on, but hopefully it'll start working. My name is Sam. I'll now introduce everyone to the semi-automated legal document analysis project, which, as Mitchell mentioned, is another internship under the Monash Data Science and AI platform. Myself and Maddie Haddad contributed to this project over the last semester under the supervision of Adam Morris, along with GUI design help from Daniel Waghorn. Current document analysis methods are often completely manual, not to mention slow and tedious. The overall goal of this project is to speed this process up as much as possible, providing help to analyze many kinds of documents, in our case, specific to law. Our implementation is currently still semi-manual, but in the future, this could be closer to or even completely automated. We have found that the user's questions about a document may often be grouped into themes, such as questions about nationality or human rights, for example, in the case of law. Each of these themes can have identifying keywords or entities that can then be used to answer the questions belonging to this theme. For example, if you're looking for the nationality of the judge, you could search for phrases involving the name of the judge first, which would narrow the information you need to sift through considerably. Our approach revolves around searching for these entities using various tools and simple search algorithms. A notable tool we currently utilize is Spatie, which is a natural language processing tool that has the ability to load models and pass text through it, such as Word2Vec, tokenization, and statistical models. The main product for this internship is our proof of concept application with its own GUI. It reads a JSON settings file containing the path to HTML documents, which were often converted from PDF. It then pre-processes these documents in such a way so that firstly, highlighting any particular word is fast and trivial, and second, grabbing sections of text is easy, with the HTML structure of the document still being preserved. For each document, we can select a theme which will have its own set of components to be searched for. Currently implemented components operate on keywords, which are a single word, entities, which are usually a phrase length, or sections, which are full paragraphs of text. The text that matches any of these components can then be highlighted and unhighlighted dynamically without needing to reload the page. The user can then input the answers to the theme questions easily once their desired information has been found. I will now pass it over to Maddie, who will explain these features further.
Thank you, Sam. Application features. The application makes use of plugins. Each plugin acts like a pipe where it takes text from one end, processes it, and then outputs the result on the other end. These plugins can be used by researchers to speed up content analysis. We currently support 3 plugins. The first one is keyword matching, which we have 2 types. Strict matching, which is searching the text for exact matches of the keyword, just like the find functionality in your text editor. The second one is semantic matching, which looks for closely related words, and the user can specify how close the related words should be. The second plugin is named entity recognizer, where one or more words are matched against entities. An example of an entity could be an instrument or a court for law documents. And finally, the last plugin is text categorizer, which is used to categorize sections within the document. An example of a category is an axiom. The user has also the ability to instantly filter plugins using the filters which are located on the bottom right corner of the interface. The design features. The application is designed to handle any model, not just legal models. In our development, we used Blackstone, which is a Spatie model for processing long, unstructured legal text. But the user doesn't have to use this particular model. They can provide their own Spatie model as long as the model supports at least one of our plugins, which are keywords, entities, and text category plugins. Building on flexibility and extensibility, the application was also designed to easily add new plugins to speed up content analysis. For example, we can easily add part of speech tagger or any other custom plugin. Future aims. Some possible improvement for this project. It could use a better solution to convert from PDF to HTML. Most of the documents that we worked with were in PDF format. We used Adobe Acrobat to convert them to HTML so that we can process them. Adobe Acrobat does not perform well for scanned PDFs. One potential solution is to use a third-party solution such as Tika or Amazon Text Extract. Automatic prefills of items. Currently answering items of a theme has to be done manually. Generalized for any document, not just law document. Even though the application can handle any model, there is no friendly way for users to enter a model manually. An improvement would be to allow for such functionality through the interface. And finally, the last improvement would be moving to a web-based application. Currently, there is a delay before processing the document. It can be anywhere from a few seconds for short documents to 10 or 20 seconds for very long documents. To speed up text processing and promote ease of use, we recommend moving to a web-based application. This concludes our presentation. I'll now hand it to Mitch to play a video demonstration. Thank you. This is the view that the user gets greeted with when they first start the application. Here we can see all the cases currently available. This is the metadata view of the currently loaded case. Here we can see all the themes currently available. These are the items related to the current theme, and these are the plugins enabled for the current theme. Each plugin has filters. Here we can see the sections. Next to the section header we can see numbers. These numbers represent the number of hits of each of the filters in the plugins. We can change the case. And as you can see, the case has been loaded and the filters have been applied to this document. An example of semantic matching, which currently the keywords is performing, is the word interest. As you can see, the application correctly identified investment and rights as closely related to interest. We can change the theme, and the new changes of this theme have been applied. An example of entity is here. As you can see, the application correctly recognized International Center for Settlement of Investment Dispute as an instrument. And that concludes my demonstration. Thank you.
We will now be hearing from our deep learning projects. Unlike the platform-led projects, these are managed within Monash Deep Neuron, though they are still supported by the Data Science and AI platform. First up, we will have Ryan to introduce the reinforcement learning team, which has been investigating deep reinforcement learning techniques in preparation for applied research in future semesters.
Thanks, Mitchell. Hello, everyone. My name's Ryan, and I'd like to introduce you to the reinforcement learning team, which involves Will McLean, Nathan Sims, Connor Vo, Scott Bennett, and myself, of course. So as the name suggests, our team is heavily involved with reinforcement learning, but specifically deep reinforcement learning, which is essentially a mash of two fields within machine learning, deep learning and reinforcement learning. The main differences between the two are that deep learning is more concerned with training from a training set and then applying that learning to a new data set, whereas reinforcement learning is mainly concerned with how an agent within an environment will make decisions over time and dynamically learn from these decisions to maximize the cumulative reward. Later on, I will explain how we combine these two to make powerful agents, but for now, let's just explore reinforcement learning in a bit more detail. So reinforcement learning is not a new field, and for those familiar with psychology, our use of reinforcement learning actually derives from their field of study. So one of the better examples I've come across of how reinforcement learning works came from a scientist, Gary Chi, who illustrated the following. So imagine a baby, which you consider the agent at the top of the diagram, is given a TV remote control at your home, the environment. In simple terms, the baby will first observe and construct their own representation of the environment, which we call a state. Then the curious baby will take certain actions like hitting the remote control, which we can classify as an action, and observe how the TV would respond, which would lead to the next state from the environment. As a non-responding TV is dull, the baby would dislike it and receive a negative reward, and it will take less actions that will lead to such a result, updating its behavior, and vice versa. The baby will repeat the process until it learns what to do under different circumstances to become happy with its actions, i.e. maximize its reward. So I know the reason why many of the team members joined is because of the potential that reinforcement learning has today due to the access we have to such powerful hardware. With applications in almost every field, with the help of robotics, RL enthusiasts from around the world have already implemented these algorithms everywhere, from automated driving of cars or piloting of helicopters to traffic light control and power management of infrastructure. And OpenAI recently even constructed a team of reinforcement learning agents to players to challenge the reigning world champion Dota 2 team, and they won in spectacular fashion. We believe that deep reinforcement learning is currently the front runner in achieving general intelligence, but we're biased, of course. To give a background of the project, at the start of the semester, the team made a conscious decision to shift focus from a singular game-oriented project, which was dynamic balancing, to a more broader view, allowing us to explore multiple environments and algorithms. This was due to the team having a huge influx of new members, which allowed everyone to sharpen their current knowledge while ensuring everyone a foundational understanding of RL. Our aim for the semester was to build and develop the team's intuition and to investigate how agents can learn dynamic policies. We believed after one project window or season of building a foundation of our understanding of the field as a whole, it would allow us to explore much more complex and exciting projects in the future. Our end goal for the semester, however, was clear from the start. It was to implement a complex, lightweight algorithm known as proximal policy optimization, which we'll get into in a bit. So our first implementation was on OpenAI's Frozen Lake environment using an algorithm called Q-learning. The goal for the agent was to safely traverse over the frozen lake surface and reach the end goal state without falling down a hole. As you can see from the legend, the S square is the starting state, the F square represents the frozen surface, the H represents holes in the frozen surface, and the G state represents the goal state, the end of the lake. So within this environment, the agent can only move up, down, left, and right, and can only observe these states, the states these actions correspond to. So for example, when the game begins, the agent will see that there is nothing above or to the left, and frozen surface below and to the right. And as the agent moves through the environment, its observations will obviously change. Through trial and error, over time, the agent can learn that moving into a hole will receive a negative reward, and that the optimal strategy is to find the shortest path to the goal without falling down. The agent does this essentially by determining how good it is to be in every given state. This value we call the Q value. And we can determine this, and it can only determine this Q value by physically entering the state. It has no prior knowledge, and remember, it can only see what we give it as an observation or state. The agent stores this Q value in its memory, or as we call it, the Q table, which allows the agent over time through trial and error to evaluate each state and determine for itself, with the given reward through the environment, the optimal strategy to traverse the lake. Although it was a great starting implementation, Q-learning is not a very robust algorithm for large state action spaces. If you think about it as if you were the agent trying to traverse a lake, in a 4-tile by 4-tile environment, you could probably remember where the holes are and the optimal strategy to reach the goal state as quick as possible. However, if you think about a new environment similar to Frozen Lake on the table, except it's a 400-tile by 400-tile environment, and you were to try and manually memorize every given tile on the lake and its Q value, it's going to take you forever to learn every single Q value. And secondly, it will take you just as long to be able to recall how good a given state is, since there are now 160,000 states. To solve this issue, we began an implementation for a deep Q network, or as we call it, a DQN. An agent with a DQN essentially uses the same algorithm as we've just brought up with the Q-learning agent. The variation being that the agent no longer evaluates and stores every Q value, and instead passes every given state through an artificial neural network, which predicts the optimal action to take. As you can tell, this is where the deep learning comes in. The agent now no longer has to memorize every state action pair and can develop an intuition regarding the best action to take, given an observation. For our implementation of a DQN, we attempted to tackle OpenAI's card poll environment. The aim of the environment is to prevent a pole that is balancing on a cart from falling on to the ground for as long as possible. This can be achieved by moving the cart left or right every time step. The issue the team faced in this environment was at the beginning of the training, the DQN tended to overestimate how good it is to be in a given state, therefore trying to determine the action to take that provides the highest Q value leads to false positives. To solve this, we implemented a double deep Q network. Without getting too deep into it, one network will give us the Q values from each action that is possible from a given state, and the other network will calculate the target Q value of taking that action, allowing us to mitigate the overestimations of certain Q values. With the double DQN, the group wanted to move on to an environment in which the agent could decipher a frame or set of frames from the environment rather than a tailored state. Therefore, we moved on to the Atari game environment, Pong. Another issue with double DQNs is they generally perform poorly in continuous action spaces, meaning a set of actions where each variable is continuous rather than a discrete value. But first, let's get into our implementation with Atari's Pong. So for those of you who are unfamiliar with Pong, essentially you have two paddles, one on either side of the screen, and the aim of the game is to score points on your opponent by hitting a ball past their paddle into their end zone or goal. In this demo that we'll be showing here, the paddle on the left is programmed to specifically follow the ball at every time step, and the paddle on the right is our agent that we trained using a double DQN. So as you'll see here, the agent seems to struggle in the first 2 points due to some unexpected states. However, after this, the agent on the right seems to get into a rhythm as it starts to pick up on what it has learned and starts to exploit the paddle on the left. This agent has developed its optimal strategy to win after approximately 2,500 Pong games, which equates to roughly 5 million frames or states observed. We've sped up the video a bit in a second, or ended it. But to me, it's always really fascinating how every agent learns slightly differently on each playthrough. I think there's a bit of a video issue, but towards the end, you'll quickly realize the agent never actually scored another point, the other agent, and we essentially dominated the game. So this leads us on to our next implementations, which are actor-critic algorithms and proximal policy optimization. With these being policy gradient methods, we can now train the behavior. Sorry, I think my headset just ran out of juice. I've charged it back up. Sorry, actor-critic algorithms and proximal policy optimization. With these being policy gradient methods, we can now train the behavior of the agent directly. For actor-critic in particular, we can now have an actor which will look at the observation and give the agent an action. And we have a critic which evaluates the action from the actor. To give an example of this, I'll use an example from AISummer.com. An actor-critic relationship can be explored through the idea of a child and its mother, where a child will constantly try new things, such as trying to eat Lego, or kick a soccer ball, or place its hand on a hot grill, and its mother will either criticize or compliment him. We first tackled the environment on the left, Atari's Car Racer, with vanilla actor-critic and advantageous actor-critic, and found that it was terribly inefficient and slow to run with just a single environment. We then moved on to proximal policy optimization, which introduced a new way of looking at loss calculations, and also the addition of environment multiprocessing. Without going into too much detail, as these require much more of a deeper understanding of deep and reinforcement learning, this development dramatically increased the rate at which we could train. But more importantly, we hit our goal, which was proximal policy optimization. Our implementations with PPO have currently included the Lunar Lander Atari game and OpenAI's Bipedal Walker, which is loosely based off of a popular internet game called Quap. So we have the quap variant here, which is called bipedal walker. Essentially, the bipedal walker agent has to attempt to travel to the right to make it to the end without falling. So ideally, we would have the guy starting to walk across. It starts well with a little push. However, it doesn't last long, and its idea of optimal strategy still confuses me. As one of our members will accurately described, the agent looks like when they make you hold a boogie board and kick with your feet at a swimming lesson. Although the ideal solution in our eyes was for the walker to walk, it seems as though after a long enough training time, with the given reward structure, it deems this to be the optimal strategy, and for that we can only admire its determination. The project for the upcoming season that has been decided upon is a chess bot. Using the skills acquired over the course of the project season, the team is really keen to apply deep reinforcement learning to the world of chess to create a proficient agent that would be able to challenge Monash's greatest chess minds. In the future, being next year, we have more exciting projects down the line that are being considered, such as MineRL, and one from our own team member, Connor, who has an idea for a financial trading agent. MineRL is a reinforcement learning-based competition that aims to get competitors to build agents that can successfully complete certain tasks, such as chopping down trees and mining for diamonds in the shortest amount of time in one of the most famous games ever created, Minecraft. The financial trading agent is essentially an idea for an investment portfolio managed by an RL agent that would be able to make decisions about certain stocks to buy/sell to increase the value of the given portfolio. Thank you very much for listening. Sorry about that little technical issue. Hope you enjoyed, and now I'd like to pass back to Mitch.
Next up, we're going to have Jared from the Microfluidics project, which has been working to determine the viability of sperm with convolutional neural networks, along with researchers from the Monash EMB lab.
Thank you, Mitch. Hello, everyone. My name is Jared, and along with Beck, Nidhi, and Sahil, we're the team for the Microfluidics project. So this is a brand new project this semester, and the aim of our work is to assist the researchers over at the Monash Applied Microfluidics and Bioengineering Lab in developing machine learning solutions. The specific area we're working in is in the space of sperm cell analysis and selection, these being particularly critical tasks in assisted reproduction, the most well-known of which is IVF. For anyone who isn't familiar, IVF stands for in vitro fertilization, and it's the most common form of assisted reproductive technology. Part of the process of IVF and methods like it involve the need to select healthy, viable sperm cells. And that's where the need for effective cell analysis and selection comes in. But there's a lot of critical problems in this space. Traditional methods for cell analysis and selection are costly, time-consuming, and they require skillful clinicians who are oftentimes employing non-standardized procedures. And we're aiming to overcome these issues by utilizing deep learning techniques to improve cell analysis. So the problem we started looking at first is that of classifying sperm cells by their morphology or their shape. This is hugely important, as along with motility or movement, it's the main way that scientists have of determining cell viability and health. There's been a number of papers in this space over the past decade or so, the most recent couple being the first to introduce deep learning into the mix, and their results have been far ahead of the previous techniques. These papers took their focus on two publicly available datasets called HuShem and Cyan. So this is where we decided to take our project first, with the goal of first matching and then beating their results. As this is a new project, our work has begun with a lot of experimentation and getting used to the problem we're tackling and the two datasets we have to work with. Our focus thus far has been on utilizing existing pre-trained convolutional neural networks and trying various ways to adapt these to meet our goals. So modern image classification models such as ResNet, VGG, and DenseNet have been our main focus so far. We started with the dataset HuShem, as this dataset has the benefits of high visual clarity and higher resolutions when compared to Cyan. HuShem has 4 classes, 1 normal and 3 different abnormal classes. The state-of-the-art performance on this dataset has been around 94 to 95.5% accuracy previously. Through experimentation and tuning of pre-trained models, we've been able to achieve as high as 96.9% accuracy, which we're pretty excited about. And then the next data set, Cyan, we've been looking at, has 5 classes instead of 4, but the main issue is that the dataset is very imbalanced. The top class has nearly 10 times as many images as the smallest class. This has been a bit of a challenge to deal with and has resulted in us having to explore balanced sampling in order to achieve accuracies that are more consistent across all 5 classes. Otherwise, it'll tend to optimize for the class with the most images. What we've found with both datasets is that different models will perform quite differently in each class. The graph on the top right here shows how for the normal class, the 3 models shown will perform quite differently over training. When then looking at a similar diagram for another one of the 4 classes, we found that each model will again be better or worse than one another in different ways. In light of this, the current direction we're taking with our project is in trying to bring together the power of multiple different machine learning models that we've investigated. And we're attempting this through a process called stacking. This is illustrated in the diagram in the bottom right, which shows how a single input is processed by multiple models, each producing their own predictions based on the input. And then these results are combined together with a meta classifier to produce a single output. The entire system is called a stacked ensemble. This allows us to harness the strengths of the various models and their varied performance across the multiple different classes. So this has been a fairly recent direction for our project, but our initial work has already been quite promising. We've been able to successfully combine multiple models together and achieve better results than any single one of them individually. And we're already confident that we'll be able to achieve substantially better results than the current state of the art using this method. In the future, there's many different directions where we're excited to take our project. Next year, we will be expanding our work to utilize more realistic data captured by the Monash AMB lab. The main issue we have with the data sets we have access to so far is that they're quite small and they suffer from some quality issues. And the cells in Husheng have actually been dyed. While this makes it easy to classify them, it does destroy the cells, which then makes them unusable if you wish to then select a cell for assisted reproduction. So having a new data set, one without these issues, will open up a whole range of exciting possibilities, including the potential for us to work towards creating a tool that would allow researchers to rapidly and accurately analyze the health of sperm cells without the need for trained experts, and then actually allow these cells to be selected for use in assisted reproduction. We're also looking to expand into a new sub-project, working instead with analyzing cell motility. We're hoping to see if we can train a model on video of sperm cells' tail movement to detect the presence of gene abnormalities. So that's just a broad overview of the progress we've made in the semester and our future directions. If you have any questions about the project, we'd of course be happy to answer them in the Q&A. And now I'll be handing back to Mitch. Thank you.
Our next project is fault location in energy grids. They have been looking into identifying the locations of ground faults within electrical grids using MATLAB Simulink simulations and long short-term memory networks. We will now be hearing from Sean.
Thanks, Mitch. Hi, everyone. My name is Sean. I'm the project manager for the fault location team. Under the supervision of Dr. Rizagi from the ECSE department, our team's aim is to accurately locate electrical faults in a power grid by using signals generated by those faults in a machine learning context. Traditional methods of diagnosing faults are often mathematically rigorous and require teams of technicians to patrol a down system section by section, which is often time-consuming and relatively inefficient. The team seeks to advance research in this field by applying machine learning techniques such as recurrent neural networks to time series data on the voltage of a power grid. Our current approach involves collecting data from a power grid model in Simulink, as shown on the picture on the left. After initiating a short circuit, this simulation will record the propagated transmission line voltage signals at different points in the power grid. Upon collection of different simulated fault types, such as a single line to ground fault and a line to line fault, to name a few. Next slide, please. We can observe different voltages responses to different types of short circuits. Next slide, please. So this is illustrated by the 2 graphs that are taken from MATLAB. The data is then applied to an LSTM, which is a popular type of recurrent neural network used for sequential data, and the goal is to have a reliable prediction of the fault location and type. In the near future, we're excited to expand our research into more realistic data and models of faults, such as data collected by the Australian government on bushfire-related transmission line faults. Most of the work done by the team this SEM has been focused on hyperparameter optimization. Hyperparameters are key design features in a neural network controlled by engineers. Much like building a house, you would be interested in the dimensions of the house, how many layers or stories you would like, etc. Hyperparameters are the metaphorical equivalent of the features of a house that deep learning engineers are building. Therefore, hyperparameter optimization helps engineers search through the multidimensional space of possible hyperparameters and picks ones that are closer to the ones that will give optimal performance. Over the last 2 months, the team has been focusing on 2 main hyperparameter optimization tools, known as blowtorch and weights and biases sweeps. As shown on the screenshot of a graph of epoch versus accuracy over several optimization runs on the right, the team has had great results with weights and biases and will be using it on the long run. Over this SEM, the team has been challenged with a more complex space of data types, such as having different resistance values in our short circuit simulations. Upon reflection, we have recognized the need to prioritize visualizing our data sample space before jumping into applying deep learning techniques. We will also be considering a new recurrent neural network architecture and attention-based models in our future designs. The team will be continuing our work over the summer, and we will continue to work on 2- and 3-phase fault location models and phase prediction models. We are very excited about our work, so if you have any questions, feel free to leave them in the Q&A, and we'll be happy to answer them. I'll be handing back to Mitch now for the meantime. Thank you.
Finally, we will be hearing from David, who works on the CT facial reconstruction project, which has been looking into reconstructing facial shapes from skeletal remains using generative adversarial networks and CT scans.
Thank you, Mitchell. My name is David, and I will be presenting the progress of the CT facial reconstruction project. The team is supervised by Dr. Xiaojun Chang and made up of myself, Mitchell, Stephen, Cameron, Peter, and Anwar. So firstly, I'll give a background of the project. Our project focuses on performing forensic facial reconstruction, which is the process of reconstructing recognizable faces from the skulls of an individual. It can be used in archaeological restoration, disaster relief, and of course, criminal investigations. Traditionally, it has been done in what is called the artistic approach, where a trained professional draws or sculpts a realistic face based on the skull. However, this is extremely time-consuming and is very subjective based on that professional's interpretation. As a result, a variety of automatic approaches have been explored, using known correlates and statistical information to map tissue thicknesses based on anthropomorphic landmarks of the skull. However, there are many parts of the face that do not have strong correlates to the skull, such as the nose, lips, and ears. Thus, automatic approaches have not been able to achieve the accuracy great enough to be used in the practical domain. We believe deep learning can be applied in this area, as it is an automated approach which can capture deeper and higher level features in object recognition and reconstruction. Thus, the aim of our project is to implement a generative neural network model to achieve a high enough accuracy in generating recognizable faces from skulls. To do this, we received a dataset of CT head scans from the Victorian Institute of Forensic Medicine. And from those, we threshold to the bone and flesh for our 3D input and our 3D label for our model. We're currently exploring 2 types of models to solve this. First, using a 3D generative model directly on the 3D density CT scans, and secondly, using pre-trained 2D generative models on 2D depth maps of the front of the 3D images. We have built both models into what is called generative adversarial networks, which is where a second model is introduced to contest the generative model by trying to discriminate between generations of that model and labels. The main focus of this semester has been on refactoring our whole system from the ground up to create an efficient refinement pipeline for parameter refinement, like the Power team has been doing. The idea of this pipeline is we can constantly run sweeps and runs on a variety of configurations on our model and data just by changing a few configuration files. We use Hydra to handle a hierarchical system of configuration files and pass those configurations to our data module to determine how data is loaded in. Our training module, configured in PyTorch Lightning, which is widely used and understood in academia, and to our model creation suite to select any one of our custom model configurations. We have to do this because 3D does not have a plethora of pre-trained models like 2D does. So in order for us to maximize our results, we've had to create our own 3D models. Rather than building these models layer by layer from the ground up every time, we've created a model creation library that abstracts all of that away, whilst giving us access to create any kind of block or feature we want. During training, the results are stored in real time on weights and biases, and because we are working in 3D, we've had to create a custom pipeline to render the 3D images in a headless mode to take a 2D image of its front. This semester, we have made a variety of improvements to our pre-processing and training. One of the main issues in the dataset is that the heads could be rotated anywhere from -90 to 90 degrees. This is particularly troublesome for our 2D depth map solution, which only looks at the front of the image. To rectify this, the team has developed a way to identify the orientation of the heads and then perform a 3D rotation. To do this, the team discovered that the teeth were in fact the densest objects in the head. Thresholding to that density and then creating a depth map from the top of the image revealed the arc structure of the teeth that gave the orientation of the head. Another major change was a refactor of how we cleaned, cropped, and downsized our data. Our CT scan images are very large, made up of 512 by 512 by 512 separate density pixels. And this takes up a lot of memory when we try to run it on our graphics cards. So to even get it to run at all, we've had to downsize the images to 64 by 64 by 64. From there, we cleaned the images and cropped the shoulders out. However, a large amount of information is lost in this downsample. So to maximize the efficiency of our information, cleaning and cropping is now performed at the original size, and then each image is dynamically downsampled after the crop, so that it maximizes the final space. For training, we've implemented feature loss, otherwise known as perceptual loss, by using an externally pre-trained model to extract feature maps to calculate loss on. For 2D, we tried a variety of popular 2D pre-trained models and found the best results using a model called VGG Face, which is a pre-trained model specifically for classifying celebrity faces on the internet. For 3D, there are less pre-trained weights available, so we've had to use weights pre-trained on the Kinetic 700 dataset. We've also implemented a variety of new evaluation metrics, such as intersection over union, chamfer loss, feature loss, and feature loss 3D to 2D, where we convert the 3D image to a 2.5D depth map and perform 2D feature loss on that. So here are some of our generations, with the input skull on the left, then the label next, which is the original face that the model is trying to regenerate. I have unfortunately had to blur these for privacy reasons. Next, we have our 3D generation from our GAN, trained with the Kinetic 700 feature loss. And then we have finally our depth map generations from our 2D GAN, trained on VGG feature face loss. As you can see, they're able to extract the general orientation of the face and get basic structure and flesh thicknesses. However, they still struggle with the ears, nose, and lips, parts of the face, which I mentioned had little correlates to the actual bone structure. Through the summer break, we have a variety of goals we hope to achieve. We hope to train our 3D dataset on a size of 128 by 128 by 128. These trainings take extremely long, even with the heavy compute on the massive computer cluster at Monash. And thus we want to have a pipeline that was fully set up before training on it. With the new refinement pipeline, we'll perform sweeps on all our learning parameters, And with the model customization suite, we want to test our new model configurations with features such as different attention layers, multi-scale gradient transfer and GANs, as well as applying techniques to force the generation of those areas that have little correlates to the bone. With the possibility of getting a larger dataset of CT scans to train on from BIFM, we want to look into pre-training on that dataset to improve our generative model or feature loss model. Then to validate our project, we'll be performing face pooling, which is where we compare a pool of similar labels to our generation and see if we can consistently recognize which face their generation belongs to. With these results, we hope to complete our research paper by March 3rd, which is the deadline for the Medical Image Computing and Computer-Assisted Intervention Conference, at which point this project will be completed. So that concludes the update for my team. And I'll now hand it over to Rebecca.
Thanks, David. I'd like to say a big thank you to all the project teams for all your hard work. each and every one of these teams have been putting in so much work and have really achieved some really exciting outcomes. I'd also like to thank all the project managers who've been giving these presentations this evening. I hope you've all enjoyed learning more about what we've been doing here at Monash Deep Neuron. Before we move to our Q&A session, I'm really excited to be formally announcing the new 2021 team lead for Monash Deep Neuron. Please join me in welcoming Scott Bennett as he takes over the leadership of the team for the coming year. Before I hand over to him, let me just tell you a little bit about Scott. Since joining the team a year ago, Scott has made a huge contribution to the team, not only just as part of our reinforcement learning project team, but also by serving as our operations manager for the last 10 months. I personally can't imagine a better person to be leading the team next year and can't wait to see how the team continues to grow under his leadership. I also have to mention that he's been working really hard behind the scenes, making sure that this evening runs smoothly. So thank you, Scott. I'll now hand over to Scott to introduce the rest of the 2021 executive management team.
Hi, everyone. Thanks for the kind introduction, Beck. I wanted to first of all take the opportunity to thank you, Rebecca, for all the hard work that you've put into Deep Neuron this year. Honestly, I don't think many people realize just how much work you do on a day-to-day basis. You'll be sorely missed on the executive team, and I look forward to seeing what great things you go on to achieve. I should also extend thanks to the rest of the 2020 leadership team, for you have all worked hard this year. Mitch, Luhan, Karina, Kelvin, Sahil. This year hasn't been easy on a lot of us, and we've really had to put in that extra effort to overcome everything that has come our way. You should be proud of how far the team has come. I thought it would be appropriate to start with what I personally envision for the coming year. I believe there is huge potential for Deep Neuron moving into the future, and I'm really excited to have the chance to explore what's possible. Firstly, I'd like to foster a strong and diverse group of people interested in artificial intelligence and high-performance computing. I think feeling like you're part of a community is extremely important, and people should feel like they have a place to belong, especially within a student team. To be truthful, this year has been hard on me. I thrive off being around people, and not having that face-to-face contact has definitely taken its toll. However, this has also allowed me to grow my appreciation for the social aspect of all the work I do. It's especially important in a student team like Deep Neuron, where we could spend all day coding in a room if we really wanted to. And it is important not to lose connection to our communities. I, for one, cannot wait to get back to campus next year and actually get to hang out with the team in person, whether it be through extra social activities or team bonding activities or just hanging out in the library. I want to deepen the connections and community within the team. Secondly, I'd like to see Deep Neuron realize their potential when it comes to producing meaningful output. We've done some fantastic work this year, with CT being on track to present a paper to a conference early next year, microfluidics already achieving exciting results after only 4 months ago, the promising collaborations between the data science and AI platform, not to mention all of the teams making strong progress in their respective areas. And I think we can do more. The fields of AI and HPC are rapidly expanding, along with the potential for new and exciting projects from a wide variety of fields. And I think we should try our best to embrace this as much as possible moving forward. Finally, I think it is important for us to strive to maximize the opportunity we give to students. Giving students the opportunities to develop and explore their passions is an integral part to why student teams exist. And we certainly shouldn't lose sight of it when making our decisions. I've split this into 2 main categories: internal opportunities to grow and develop through working on projects, internal training, professional development, leadership opportunities, and so on. There are also external opportunities like internships and grad jobs, which will hopefully come from continuing to develop our network between Deep Neuron, industry, and academia. As many of the people can probably tell you, I can talk on this for hours. I find it really hard to nail down my ideas to concise points, but hopefully that gave you a rough overview of my ideals moving forward into next year. And again, if you have any ideas on how you might be able to collaborate or help Deep Neuron grow and prosper in a community in general, feel free to reach out to us. We are more than happy to try and take on new ideas and initiatives. And for any student who might be listening and wanting to get involved, we run recruitments at the beginning of every semester, which you can see our website for more details. Anyway, now onto the main event. I now have the pleasure of announcing our newly elected 2021 Executive Management Team. As the Deep Learning Lead, we have Will McLean, who will now say a few words.
Thanks, Scott. Hello, everyone. My name is Will, and I'm the Deep Learning Branch Lead for 2021. I'm from the Reinforcement Learning team, where I've been a member for the last 6 months and really enjoyed my time. As Deep Learning Branch Lead, my role is to sit on the executive team and also to manage the Deep Learning project teams. For 2021, I'm really excited to set up some new interesting projects and to make sure that Deep Neuron is the best possible place for all members to learn. Please always feel free to give me an email if you've got any questions. I'm always open for a chat. Thank you, everyone. I'll pass back to Scott now.
Once again, congratulations, Will. I'll now have the pleasure of introducing Yusuke Miyashita as our High Performance Computing Lead.
Thank you, Scott. Hi, my name is Yusuke. I'm very excited to contribute to the team as HPC lead. My role is to check on the progress of each project in the HPC branch and make sure that project members can focus on the technical side of the project. I'm also in charge of coming up with a new project. Currently, there's only one project in HPC branch, so this is something I would like to work hard on my term. I'm also hoping for more collaboration between Deep Learning branch. Thank you.
Thanks, Yusuke. I'm definitely excited to get the chance to work with you, and will hopefully be pretty exciting 2021 for the HPC branch. I will now introduce our operations lead, Nathan Sims.
Hi, thanks, Scott. Hello, my name is Nathan. I'll be filling the role of operations lead in the coming year. I'm a mechatronics student, also currently a member of the reinforcement learning team, and I've already learnt so much as part of the team. I'm super excited to take on the role as ops manager to be able to assist in the managing of the general operations of the team, as well as overseeing the newly built marketing component of the team. I look forward to developing myself and working as a part of this great exec team for 2021.
Thanks for that, Nathan. And finally, we have Connor Vo as our business lead. Congratulations, Connor.
Thanks, Scott. Yes, I'm Connor. I'm a fourth year mechatronics engineering student, and I'm really excited to be on this executive team, this very capable team. So Deep Neuron has plenty of growth opportunity in terms of our of building credibility with members of industry, and I'm very excited and have plenty of ideas for this role. Thank you.
Thanks, Connor. That completes our formal presentation for the night. I hope everything learned something new. We will now be heading into the Q&A section of tonight's program. For those who have any general or technical project questions, now is your time to ask them. This will be led by our 2020 Deep Learning Lead, Mitch, which you would have met before. But before I welcome Mitch, I would first like to take a moment to thank everyone who has attended tonight's event. I should also extend a special thanks to the ongoing support from our supervisors, alumni, and friends of the team in both industry and at Monash. Be sure to follow us on our social media page to get the latest updates of our work and recruitment. And if you're interested in getting in contact with us, you can find more information on our website, or you can message us through Facebook or LinkedIn. Now on to Mitch.
Thank you very much, Scott. I wish you all the best for leading Monash Deep Neuron into 2021. So as Scott mentioned, we're now moving into Q&A time. I see there's lots of questions. It's looking like we're probably going to have enough time to get through most of them. So I'll just be going through project by project. Because this question was asked first, let's start with the HPC team. So Yusuke, how much do you expect your work to speed up the processing of the inputs?
A good question. If we use MPI, that means we use multiple computers to process the data. If you use, so intuitively thinking, if we use two computers, we can use two computers to process the same data at the same time. So we might expect to increase the process time by 2 times, but there's also some time consumed by the communication between two computers. So it's really hard to predict how much time we can improve by doing the parallel computing. But what we do is we try to optimize the code by using different ways, like using GPU or compile the code into a compiler to optimize the code.
Do you think it's fair to say that it would be a linear progression? So as you add the number of nodes to your network, which is doing the processing, it'll increase, but not necessarily one-to-one. Is that what you're saying?
Well, I guess it's not, because if there are more computers to for the communication, that means like more congestion between sending messages. So I don't.
Does this mean that eventually you'll reach some kind of bottleneck in the network, and that's the maximum that you can do with the parallel compute?
Yes, that's what I'm expecting.
Okay. And a question for Luhan: how do the students connect their computers to the HPC?
Right. If you are a member of Deep Neurons, then we will set up access to our campus cluster, and we will also be providing the training. But the HPC resource at Monash universities is generally dedicated to the research activity, and is generally not available to the public. So if you want to learn about HPC, I believe outside of Monash there are public cloud resource like Google Cloud, and they will have a very similar environment to what we have been using at Monash. Does this answer the question?
It does. Thank you very much, Luhan. So next, we have a few questions for CT facial reconstruction. First up, are there any ethical concerns with how these improvements in our model is going to have unintended consequences?
Yeah. Ethics is obviously a very difficult kind of field, and so there's probably going to be a lot of people that disagree with my thoughts in the area. So when I'm looking at that question, it seems to be focused on the actual technology that we're developing. So the way that we're trying to create technology that can go from bone to a 3D facial generation. So the actual direct use of that technology, I don't see too many ethical concerns, because getting someone's bone or CT scan is quite difficult. Like, it's fairly secure and locked away. I guess the more extended kind of implications of our study is just the idea of creating realistic generations. Could potentially have ethical concerns in the future, because you could potentially use it to fake evidence, because we use so much of what we see as like the ground truth of evidence that we trust. So it's the same problem with like videos and that sort of thing. And there's also obviously a host of ethical concerns about using a neural network model in the field of forensic facial reconstruction in general. So far, an automated approach hasn't been used, but like, as you can imagine, if it was ever to be used in a criminal investigation, the idea of using an automated model that could potentially have biasing based on its data, like if we, for example, all our images came from Caucasian people, then maybe it could only generate Caucasian generations. And obviously this has huge problems if it is ever used to actually arrest someone, or actually used in an actual law enforcement kind of situation. So there are huge implications. So our projects mostly are just going for research and not for actual development of the technology at the moment.
David, would you say that then making sure that we're being as transparent as we can with our results and the limitations of that is going to be one of the key things about how we move forward with this project?
Absolutely, yes. So I think we should mention all these in the research paper, and we'll be transparent as much as we can in our results without actually showing the data itself. So our data is still going to be ethics locked. So even when we do show our results, we will not be showing the original labels, the original faces of the images that we got from BIFM.
All right, thank you very much, David. The next question that we have here for you is, how did the model perform on patients without teeth? Or who potentially have deformed jaw or some kind of different bone density?
Yeah, so currently our data set of 350 images, I think only about 5 to 10 of them didn't have teeth. So not a large enough sample to actually affect our model too much. In general, looking at the generations of the individuals that didn't have teeth, it didn't seem to have too much of a difference. As you could kind of see from our generations, it was mostly just getting the general structure of the head. It wasn't getting any of the more intricate details that it might rely on the teeth actually for. So for just getting like the general jawline and the head structure, it didn't really need to use the teeth and didn't seem to be relying too much on the actual teeth. Of course, the main issue of them having any strange jawlines or teeth issues was in pre-processing when we used the teeth to rotate the heads into the right direction. So that was flagged by the pre-processing team. All the ones that didn't have teeth was flagged so that we would rotate them automatically. Rotate them manually instead of automatically, pretty much.
I think another thing to keep in mind is that you could probably also automatically work out whether or not there are teeth, and then from there use some other kind of processing. Is that correct?
Yeah, that's correct.
Excellent. All right, so the next questions we have are for microfluidics. This is a question from Bailey. If the HuSHM dataset only has 226 images, how can you be sure that your accuracy is actually better than the state of the art and that it was not a statistical chance?
So this is related again to a question from Sam as well, who also is asking about the size of the dataset. So dataset size has been a bit of a challenge. They are relatively small for what you should be using. Ideally, for something more complicated like a classification challenge, you'd be wanting a data set in the thousands or tens of thousands of images. Since it is a pretty small problem where most of the images look pretty similar, it's going to work a little bit better, that they're quite similar visually. But the way that we ensure our accuracy figures are more accurate is by using a couple of methods. First one of which is five-fold cross-validation, which involves splitting the data set into 5 groups and then doing 5 runs where each time you will select one of those groups to be your test set and use the other 4 for training. So it's never going to be seeing the test set you selected in that run. It's only going to be training on the other 4, and then you see what accuracy it gets on the test set. And then you're going to be doing that multiple runs 3 or 5 times over and averaging the figures. And that's how you can get a more reliable accuracy figure.
All right, thank you very much, Jared. Another question for you. Do you train all of the models simultaneously, or do you combine them separately after training with an extra model after that?
So potentially you could train them entirely in one thing end to end. We haven't done that yet. Right now, what we're doing is we are training them individually, generating output data in just CSV files, and then we feed those into a meta classifier later.
Okay, thank you for that. We also have a question from Elizabeth. In terms of using video data, how is tail movement related to gene abnormality?
We haven't explored that too much just yet. We haven't started on that part of the project. I believe that it is understood that you can tell gene defects from the tail movement, as in just simply the movement will look different depending on if there's certain, I think 4 different gene abnormalities they could have. And about what types of deep learning models exist for dealing with the extratemporal direction, what you can essentially do is you can just use the same convolutional neural networks, but you would expand them into another dimension. So if normally you'd just be dealing with one image and training on that, you would deal with it so you're training on all the images stacked together to generate kind of like a 3D shape. So that is the video reference or sequenced into individual frames, and then you train on that in 3 dimensions rather than just 2 dimensions.
Yeah, just to add on to that, you can also use an approach which is similar to what the Power team has been doing, which is that you analyze it as a time series, only instead of having a 1-dimensional time series, we now have a 2-dimensional time series. So instead of some kind of voltage trace, now we have a series of images, but the principle is exactly the same. I think that's it for the microfluidics questions. So moving on to Power, is there any reason, Sean, that you guys use MATLAB instead of some other open source alternative?
Well, currently, the project's in the proof of concept / research stage. So we are using MATLAB / Simulink as a tool to just simulate a power grid model. In the future, we will be applying the same techniques to software that are used by power professionals that are used on a professional scale. Hope that answers your question.
All right, thank you. Okay, so can you give us an example of how the voltage signals might change depending on the different types of faults?
So there are generally three types of faults that we're looking at. Single phase to ground. So you can think of it as one out of three transmission lines somehow having a short circuit to ground, phase to phase. So two wires touching each other, causing short circuit between two lines, or three phase to ground, which is maybe a down transmission line where the entire 3 out of 3 transmission lines are hitting shorting to ground. And generally these different types of faults will create different transient responses, and it will cause or give different frequency components in the fault signal. So we're hoping to capitalize or exploit that feature and generate a accurate neural network that can predict that.
Thank you very much, Sean. The last question that we have in the chat is from Sam. I noticed on your website there is another project for approximating aerodynamic simulations. So this isn't an upcoming project. This is actually an old project. The reason why there wasn't a presentation on that today is because we weren't able to continue any further with it due to data constraints, essentially. Because we were mostly interested in three-dimensional data, there wasn't enough of it around along the sorts of differences that we were interested in. So we weren't able to continue with the project without spending a lot of time trying to generate lots and lots of data. So that's why that project ended. We have one last joke question, which is, why doesn't my internet work when the power is out? And the answer is, you need power to connect to the internet. We have one last question, actually, more coming in. Why did it have to be 3D and not 2D? Can we have some more information, please, about that question in the chat?
I think he's talking about the facial reconstruction.
Oh, sure. Okay, David, would you like to talk about that then?
Okay, so we're actually exploring it in both 3D and 2D. We're thinking that it'll probably in the end work better. Well, it should in theory work better in 3D because there's more information captured in 3D. Even though we're only looking at the actual face, we're only looking at the front of the face. In 3D, it's also able to capture information like the density. It's like how thick the actual bone of the of like the front of the skull like kind of area is, and like what kind of density those bone areas are, and then try to extract information from that. So we're not too sure how important that is for actually generating the generations, which is why we're exploring the 2D method as well. And one of the main benefits of exploring 2D is, of course, we have a much larger amount of models and pre-trained weights to use. But we can't rule out that there could be information that's stored in the 3D density maps that could be beneficial in the end if we can just create models and weights good enough to actually generate on that. So that's why we're exploring both at the moment.
Okay, thank you, David. Now, so we've had Bailey come back, who's actually talking about the aerodynamics project. Beck, would you like to answer this question?
Sure. Thanks for the question, Bailey. I was previously on this project before we unfortunately had to discontinue it. We did look at the avenues of generating 2D rather than 3D data. However, we found that this was also going to be quite a time-consuming process, given that we want to give our members opportunities with deep learning rather than with running manual simulations for hours on end. We decided that it was not an appropriate project for Monash Deep Neuron as a whole. It might be something that we come back to in the future, but only once we have more data provided to us rather than having to do that manually ourselves.
Just to add on with that, the question also adds, isn't there lots of situations when a 2D simplification is valid? And I think the answer is probably yes, but the specific interest that we had was with three-dimensional aerofoils, where if you were to only do a 2D CFD simulation, then it loses a lot of that information. There's no particular axes in which you can cut it and get a valid, I guess, representation. So that's why that project ended. We have another question for you, Jared, with microfluidics. Was cross-validation used for hyperparameter tuning? And if so, wouldn't the final accuracies be overconfident given that the test data has been used to choose the hyperparameters?
Yes, it was. And I understand what you're asking. We have been wary of, I guess, what is potentially implicit test set overfitting in some of our work. We believe what we're doing is still consistent with what's been done in the previous papers, so we think it's still valid. We're trying to be in some ways careful with that though, but it was used for the hyperparameter tuning. It was, yeah.
Okay, thank you. I think that's all of the questions then. Thank you everyone for coming to our presentation today. And I wish you all a lovely night.